Hello, Advanced Algebra 2. Welcome to the Concept 30 Notes Part 2. We're looking at arithmetic sequences and series. And in this part, we're going to focus on series. All right, so remember from Concept 29 that when the terms of a sequence are added together, the resulting expression is a series. So a series can be finite, it can have an end, or it can be infinite. Keep on going. So here's how to write a rule for a series. We're going to use something called summation or sigma notation, and we touched on this in Concept 29. So for a finite series, one that ends, you use the sigma, and then the lower, below the sigma, you have I or K, and this, or N, is just a variable to stand for the position numbers. And so you say equals whichever position number you're going to start at. Normally, the series will start at 1, but sometimes they don't. And then the top number is the number of terms that you will have in your series. And so if it's a finite series, you will actually have a number for n. If it's infinite, you will have infinity. And that's where 1 to n are the number of the terms in the series. For an infinite series, you'll see that the numbers range from 1 to infinity. And then notice just out to the right of the sigma, and that's a Greek letter, you write the rule. So here's an example. We have the finite series that we looked at in Concept 29, 2, 4, 6, 8. And well, it's a series now because notice that there are addition signs. So it's 2 plus 4 plus 6 plus 8. We're just not listing those terms. So in sigma notation or summation notation, our n values would go from 1 to 4, and we're actually using I. And then our rule is 2 times n, or we could also say 2 times I. I typically use the variable that I used for those position numbers. Now for an infinite series, see what's going to change is that we have the ellipse at the end of that sum, and then we range from 1 up to infinity, and our rule is the same. Now for both series, the index of summation is I, lowercase I, and the lower limit is 1. The upper limit for the summation is 4 for the finite and infinity for the infinite. And just like I said, summation notation is also called sigma notation because it uses the uppercase Greek letter sigma. So these examples will help you know how to write a series using that summation notation. So we're going to write each series using it and then find the sum of each series if possible. So first we're going to write it, then we're going to come back and find the sum. So let's write the position numbers below the terms in this first series. So 1, 2, 3, and then I noticed the pattern that the term is 25 times my position number. And so I looked at my last term, which is 250, and realized that if I divided that by 25, I would get 10. So I can tell that this has 10 terms in it, this series does. So now to write this in summation or sigma notation, I'll write my sigma. I'm going to use I, and then it ranges, my terms range from 1 to 10. Now my rule is 25 times my position number, which I'm using I. All right, now we'll come back in a moment and find the sum of this. So now I look at my second series, and I put my position numbers, and these just keep going, so I make note that they go to infinity. I write my sigma notation, and so my terms will go I equals 1 to infinity. And I notice to generate this series that I have the position number over the position number plus 1. So I over I plus 1. Now for C, I write my position numbers, and I notice that it's 5 times my position number to get my term. So 100 divided by 5 is 20. So I can tell that this series has 20 terms. So I goes from 1 to 20, and then my rule is 5 times my position number, 5i. Now, finally, for D, I've got a mistake. I need to change that 27 to 17 there. And then if you look, notice that the numerator is the position number squared, and then the denominator is the position number squared plus 1, I believe. So it goes from 1 to infinity. And so it's I squared over I squared plus 1, changing that to 17. If I had left it at 27, you'd never be able to figure that out. All right, now let's go back. So A is a finite series. It has an end. So let's write the terms. 50, 75, 4 times 25 is 100, 125, 150, 175, 200, 225, and 250. So adding those all up, you should get 1,375. On your calculator, under the math menu, if you go, and this is on the TI-83 or A84, at least the 84. If you go under the math menu all the way down to choice 0, it will say summation. And so you are able to enter in the sigma notation and then find the value of a series. Now we can't find the value of B because it is an infinite series, but C we can. So I'm going to generate these terms, 5 times my position number, and then add them up, and I get 1,050. You can also hunt around and find your sigma notation and enter in the values. When I see you in class, I'll show you how to do that. D, we can't find the sum because it is an infinite series. So the index of summation for a series doesn't have to be the letter I. Any letter can be used. Often K is used, N is used. Also, the index does not have to begin at 1. So for example, the index of the example below begins at 4. So let's write this, and it goes from the 4th term to the 8th term. So that would be 3 plus 4 squared, which is 19, 3 plus 5 squared, 28, and so on, all the way up to the 8th term, 3 plus 8 squared, which is 64, 67. And then you can just add them up and get that the sum of the series is 205. You could also use the summation keys on your calculator and put in that, and it will give you the sum. So let's return to the apple stacking problem from concept 29. You worked in a grocery store, you work in there, and are stacking apples in the shape of a square pyramid with 7 layers. Write a rule for the sum of the number of apples in each layer using summation notation. The first layer is 1 apple. On top, the second is 4, and the layers continue in a like manner. So we know that it was n squared, or now here I've mixed my letters. I have I equals 1 to 7, and then I used n, but that's okay. We will just roll with it. So for each layer, the apples that are there are the layer number squared. So if we generate those terms, 1 squared is 1, 2 squared is 4, 9, 16, 25, 36, 49. Adding them up, there will be 140 apples in that stack. Now here's how to find the sum of a finite arithmetic series. You can add them up, you can use your calculator, and there's also a formula. So what I've done is the formula is right at the bottom of the box. So let's go through that formula. The sum of a finite arithmetic series, so capital S, means sum of n number of terms. Finite means it has a specific number of terms, equals n, the number of terms, times the first term plus the last term, all divided by 2. Now, what I've got above in the box is a derivation of the formula, so how it was derived. When we're in class, we'll go over that together. Let's use that formula to find some of these sums. So we can see that they're all finite because they have a top number. That means they have a limited number of terms. So our first series has 20 terms. I'm going to pick out what I need to know to use my formula. So I need to know how many terms. So n is 20. I need to know the first term, so I plug in 1. 3 plus 7 is 10. And I need to know the last term, so I plug in 20. 60 plus 7 is 67. Now to use the formula, so the sum of my 20 terms equals n, which is 20, times a sub 1 plus a sub n, so first term plus the last term, divided by 2. So the sum of this first is 77. Now let's look at the second one. We have a series with 20 terms, and our rule is it's arithmetic. These are all arithmetic. So -4 times our position number plus 6. So n, there are 20 terms. My first term, I plug in 1, and I get 2. And then the last term, the 20th term, I plug in 20, get -80 plus 6, or -74. So using the formula, the sum of the 20 terms in this arithmetic series is 20 times 2 minus 74 divided by 2, which will give us a -720. And yes, sometimes the sum of our series are negative. So C, let's just try it again. We need to know how many terms, which is 10. The first term, plug in 1, is 9. The 10th term, plug in 10, it's 90. So the formula, the sum of the 10 terms in this is 10 times 9 plus 90, or 99 divided by 2, which is 495. All right, one more just to seal the deal. So our number of terms is 12. Our first term plugging in 1 is 9, and our last term plugging in 12 is 86. So the sum of our 12 terms is n, which is 12, times 9 plus 86 divided by 2. So the sum of this is 570. All right, that concludes the notes for arithmetic sequences and series in this part 2, Concept 30.